Hi, I'm Seunghwan Lee, and I will talk about learning temporal point process via reinforcement learning. Contents are follows. First, introduction, and next one is preliminaries and RL framework and model of the paper and learning process. The last one is experiments and discussion about it. First, introduction. I will talk about temporal point process first. It is ordered event data in continuous time, like occurrence of crime events, earthquake, patient visit in hospitals, and citation per time of paper. Uh, Typically, reproduce of those event data like called trajectory. We will use MLE, maximum likelihood estimation. Use MLE, we estimate some parameters of the trajectory and reproduce it. It has some disadvantages. First, it cannot monitor the goodness of fit, and the next one is it has some risks of model misspecification. So the author gives some RL frameworks. The generation of each event is the action taken by a stochastic policy. For details, I will explain later, but the action is time interval between two events and treat observed event distribution as the data from the experts. It is assumption. The real data set comes from the expert policy. So we mimic the experts using policy gradient with RNN. First, introduction about the whole procedure of the paper, not the whole, but the scheme of the procedure of paper is shown in this picture. Pi, real data is generated from pi. This is assumption, and using this, learner policy learns from it. First, we learn about the reward, and using this reward, pi mimics the expert policy pi a. I will check about the double stochastic point process is model to model this learner policy pi. We use RNN, and RNN as parameters. So each has stochastic neurons, which means when we will fed to RNN, we use those stochastic data into the hidden layer. So hidden layer becomes stochastic. So I will mention about the double stochastic point process, and the other says that also the reason why that is we use stochastic data and as input of RNN. So details are following in later page, and So, details of MLE is follows. First, from data, the method fit the model parameters. It is too restricted, and some other calculation problems has some calculation problems which are inter intractable integrals and miss specification of the model and so on, and it is approximated model, but it is robust approximation. So modification of MLE is quietly used in these days. uh, it has characteristics. First, it has some non-parametric forms and RNN, and it might be use RNN to model it, and still use maximizing the likelihood. So those are problems are remaining, and other method is use GAN. Uh, GAN is composed with generator and discriminators. Uh, First, using RNN, it generates some from the po- pos- Poisson process to target event sequence. So RNN, which is transformed from Poisson process to target event sequence, is a generator, and discriminator is another RNN. Detail is not written in paper, so I will skip this version of the paper, but it is the paper's algorithm is better than GAN with MLE. Also, it has some issues about computationally intensive, because RNN requires many iterations, and 2 RNN has 2 RNN is used in this procedure. Preliminaries are given in this page. First, I will talk about details of temporal point process. In temporal point process, there is history like this form. T1, T2 is event time of the event. So in less than t or second or minutes, any time units can be used. In this paper, I will use second. So in t seconds, tn n number of events are made from any source, and this is event time of the n events. So to define this procedure, we use two concepts. Uh, First, intensity function and survival function, and survival function is from the intensity function. So I will cover this first. It decides the characteristic of the sequence, name of the sequence. So in Poisson process, lambda is constant, lambda 0. Hawkes process is lambda 0 plus some exponential of the time interval. So the occurrence of past events will boost future occurrences. So in this Hawkes process, occurrence of the past events will boost future occurrences. Also, the next one is survival function, which is defined from the intensity function. Intensity integral of the intensity function, exponential of it. It uh, it is defined that conditional probability that no events in Tn and T and Tn is survival, so it is called survival. So likelihood of the observing events at T is Ft bar St, and it is product of those functions, and joint likelihood distribution of St, history St, is this one. Probability of the St is okay, intensity function, product of intensity functions and the survival function of whole the intervals, because of the uh, because each probability, it will product two terms. It consists of product of two terms, so exponential is become summation when we product exponential in above upper terms becomes summation, so we we get all the term from 0 to t. Also, we have to define some vector space which is called reproducing kernel Hilbert spaces, RKHS, because of the find some it is used to find reward and optimal policy. So I will explain it. Hilbert space is inner product space with completeness of Cauchy sequence. The definition is not important in this paper, so I will skip it. And about the RKHS is has some additional conditions on the to the Hilbert space, which is following. Hilbert space of functions f from tau to r with inner product, because it is inner product space, so we can define some inner products, and this definition follows. We made some inner products and functions following those properties. First, reproducing property is this one. Inner product of f and k kernel of the space is ft. So reproduce of these f from inner products. So naturally we can input f to k is k t t plus t prime. Next one is so this is reproducing property. It will be used to get some expectation calculation. So I will mention about this formula later. And commonly used kernel is following. K t prime is Gaussian kernel, and the polynomial kernel, these are three or 13 or 23 maybe, I think. And the reason why we define it is this is scheme of the procedure. I will explain later in details. uh, Mu is some like mean or expectation of the kernel, and is defined by this form. Also, using those formula, can we can get real function more easily. Optimal policy pi theta star is in reinforcement learning framework. We have some optimal policy pi theta star. It is when weird is given, optimal policy is represents I we can get optimal policy from those formula. It is in trajectory we have some reward, and expectation of this, and maximum argmax of in the set of candidates we can get some optimal policy. When RT real function isn't given, we have to use given expert policy to uncover this optimal reward. So optimal reward is from those formula. It is this formula is from inverse reinforcement learning, and maximization of this first term is represents the trajectories, expectation of trajectories from experts, and next one is learners trajectory and its expectation, and maximization. When difference is bigger, the reward is bigger. When difference is smaller, reward is smaller. Because we want to mimic the expert policy, so this one is from the J pi set J from pi experts, and it is from pi theta, which is learner. So when difference is big, we give bigger reward to become uh, become the same become same. And when when it is similar in first, we give small reward to do that event. So reward is a very good definition, has some good definition. Use it, we can find optimal policy from it. Calculation of those part is heavy, time consuming, so choose some approximated version. I will explain later. Model of the policy network is followings. To capture nonlinear and long-range sequential dependency in temporal point process, which is called TPP, we use RNN to analyze it. So AI, which is action from the stochastic policy, which has A is mean, and the parameters A is not mean, sorry. A is represents of actions, and this is parameters, which define or which decide the uh, probability of action A is theta. It is the nonlinear function. It is deterministic, and it is stochastic from the distribution. It is stochastic, and because AI is stochastic and besides nonlinear deterministic, we have to update those V and W. So from this, first H0 is just node, and it is fed into A1, and it is fed into H1, and repeatedly use those A and H. So it is stochastic and double stochastic because of the first stochastic part and second stochastic part. So double stochastic policy, because we have to explore more time reason, so we use doubly stochastic version of policy network. I will explain in the previous slide of this. And so weird function class, about the weird function class, and alpha is maximization of the difference I was explained, and I explained about those terms, and to directly quantify it, it means we have some, when we want to get approximation of those terms, we have used some math. And first, f is from in this formula. F is a set of a unipole in RKHSH. It means R is contained in some unipole in H, and it is transformed to the any value from the by some functions. And second one is for simple notation, pi and mu is defined by this. Pi is the integrate through the probability into some kernel, and the mu is expectation of pi, and use this notation j pi, which we will get some maximization of it, is expectation of those terms, and those terms is from those definition. It is reward and inner product of reward and kernel, and integration, and it is defined as this. So top equation is becomes those forms. Just min max problem of the this part is more precisely it is procedure of finding pi theta, not r star. R star is from this equation. Pi star will parallel to the mu pi e minus mu pi theta, so we will have this form like this. So reward can be empirically evaluated by data. This is empirical calculation of expert policy and also learner policy. So we can summarize it, hold the problem to this form. We want to find this argument of D, and D is maximum expected cumulative reward discrepancy between pi e and pi theta. So D is defined by this empirical term. Analytic solution for D is given in this form. It is same R star, and to find this R star we will represent this form to this. This form is approximated by this form from empirical data. Also it is bias, so I will handle this bias data later. And so learning via policy gradient from this. So we our problem is the argument, find argument of D is from the empirical data from which is given data. So instead minimization of D we use D square. So gradient of D square is given in this form, and the to reduce the variance of to reduce bias or variance, not the bias, variance of the gradient, set baseline BL, abstraction of the some value to this form, and learning algorithm of the whole learning algorithm is given in here. First, it is mini-batch reinforcement learning for learning point process, which is called RLPP, and initialize model parameters, and for numbers of training iterations we do sample some mini batch of L trajectories from experts and mini batch of M trajectories of events from learner policy pi theta, and estimate policy gradients pi theta d square as this form, and it is given from the RNN like this form, and it is given from the data and empirical form. So the update policy parameters in the policy parameter in RLNN to this method, and we handle some running rate. So experimental results are given in this page. First, about reward function. We have some intensity function difference in this left figure. When the difference, when we want to some, we want more or less sorry we want to less results in this less than 10 seconds, and better results bigger than 10 seconds. We set not set, we can get some reward function like this form. So we have matches expert and learner policy, and reward becomes 0. So we use some the other use some data sets first, synthetic data sets, to show the robustness to model specifications. It is a problem when we use MLE. In homogeneous Poisson process is like this form. Intensity function is AT plus B, which is inhomogeneous in time, and Hawk process is synthetic data sets. So we model this from A and B and alpha, a mixture of those processes, and mixture of those processes with multiplied coefficients. We randomly choose those coefficients, and real data sets are following. First, 911 call data set, 220,000 crime incidents, and Microsoft Academic Search (MAS), which provides information about citation records for 50,000 papers, and medical information marked for intensive care. I don't know what it is, and it is visit record for hospital about the patients, and NYSE is trading record, which is from the economic market. So the experiment results are following. First, the blue line is real data sets, and the RLPP is the red, I think, and the sky blue is the SC. S is from the other method. I think it is MLE, I think, and the other method is MLE plus some other method like GAN or Gale or other, and it does not fit to the real data without double GAN, and this data double GAN cannot fit the real one, and the RLPP is the best, gives some best result in this procedure, and it's a second best, or I think second best. And the IP plus HP is in IP plus HP, maybe the SC method, not the RLPP is the best, and the RLPP gives some not the best but good result, and RLPP in IP plus HP2, it means we use coefficient 2 to the dataset, and sorry, it 2 means changing coefficient with some randomly chosen coefficient. So in real data, this form intensity and time has some this form, and RLPP tracks these experts and the best result. And 911 calls in real data, this form and RLPP is the best fit to real because of those parts and those parts. And the MAS gives also the at least second best. Also mimicry gives some best, and NISC, when NISC it gives third best maybe. So in conclusion, RLPP is best among the whole datasets, and comparison of runtime is shown above. Also, but sometimes MLE gives better estimates and better estimate for the true parameters. In the paper, it just mentioned, not there are not details. So this is it. Thank you for listening. And question, is there any question about it?